For the first talk in this second session, we have Dr. Titus Winters, and he is a senior staff software engineer at Google. He is the library lead for Google's C++ code base. For the last 10 years, Titus and his teams have been organizing, maintaining, and involving the foundational components of the Google C++ code base. It is really amazing to have a representative from what you call the industry, and like from Google, it is just amazing. Thank you so much for being here. And Titus, the floor is yours.
Yep, I'm very glad to be here. Thanks for having me. So this is going to be a little bit more software centric, but I think some of this should apply, I think. The very description of this seminar speaks to me at a deep level. Of course, we need reproducible research results to advance our understanding. That's science. And of course, we need to include source code and software in that. Software has continued to weasel its way into the very fabric of society, and our scientific endeavors are no different. So I'm completely on board with all of the aims here. And then when it comes to the specifics of how do we make research results that depend on software be reliable and reproducible, and to make that last as long as they are needed, then you're suddenly asking questions that I have spent much of the last decade thinking about while being responsible for the care and feeding of Google's C++ ecosystem. That is roughly 250 million lines of code with 12,000 engineers working on it in any given month. That said, I was not always a professional. Before coming to Google, I cobbled together a PhD out of hacky scripts and sort of one-off analyses. With the benefit of hindsight, I'm positive that I would not be able to reproduce the stats in my dissertation. After I graduated, after my PhD, I worked at a consulting company that was a lot more professional, and I got at least a little bit of exposure to modern practices, code review, testing. But even there, things were perfunctory and testing was pretty minimal. So I've seen a few points on this sort of reliability and reproducibility spectrum. But one critical realization underpins all of the advice that I'm about to give, which is software engineering is not the same as programming. We all start in the same place. We learn to write code, usually to solve a problem, to do a particular bit of analysis, to tweak our data some way, to filter some things, to do some stats. And that's important. Like, that is a difficult skill and that is a useful tool. But software engineering as a distinct discipline has known for 50 years or more that that is different than programming, or that is different than software engineering. Software engineering is what happens to programming when you add time and other programmers. You're not just producing some code, you're not just getting it to work one time, but you're producing code that works across time and for other people. And as it turns out, to my mind, that's exactly the topic of this seminar. You need your research code to be reproducible, whether that means some other researcher rerunning the analysis, or you picking up the software again after a few months or years to check if your results still hold. Software engineering is the multi-person construction of multi-version programs. And that definition goes back 50 years or more. We're just talking about time and people. Interestingly, research code has always been sort of the go-to example of this is mostly a programming problem, right? This is a problem where you're probably the only one working on it, and in many cases, you're going to try some things and throw it away, and that's fine, right? But as we start having this reliability crisis or reproducibility crisis, we're seeing that reliable and reproducible research code may need to pick up some of the practices from software engineering. And thus, I'm here to give some suggestions and reasoning about where to invest, where to focus your energies to try to get a good bang for the buck on sort of leveling up your game. What practices you should focus on to make the transition from, I got some results, to, I have reliable and reproducible results that other researchers can also validate, both now and in the future. I also feel compelled to throw out the standard reminder. We have known in tech since the 70s, there is no silver bullet. Anyone that pitches just use this one thing or just follow this one practice as a magic solution to anything in software or tech is not to be trusted. No one thing here or anywhere in this topic is going to be make or break, but each of them do matter individually, right? We can do better, not as one giant leap, but as many small steps. Improved results come from the aggregate impact of many small changes. I wish that I could give you one true answer, but that is not how this works. And now if you'll permit me, I need to geek out a little bit and take a little diversion to help motivate testing. If you've ever watched Star Trek, anytime anything happens when they're out in space, they pretty much instantly know what's up, right? They say, oh geez, we've lost power on decks 3 through 5, or shields are at 50%, or at most, they have to say, run a level 4 diagnostic. As it turns out, this is actually the system design that we're looking for, right? You don't want to send a runner to every deck to see if the power is still on. You want important events and changes brought to your attention instantly. And you don't want to send a team of people to investigate every random feature of a starship to see if everything is still working. You want a one-stop mechanism to see whether something is broken, hence run a diagnostic. Compare for a minute. If you're building something very simple, a bicycle or a script that does a very simple sort of statistical analysis, you can probably remember all of the things that need to be tested to be sure that it's working correctly. And if you're very, very responsible, you might even remember to do that reliably. But even for bike maintenance, there's a lot of details in here, right? I pulled this list off of a Google search, and this is wildly simplified. The actual first hit on Google for this had 300 words describing stuff that needs to be done before and after every ride, as well as weekly, monthly, and annually. Practically speaking, I suspect very few of us are doing this fully, and we're not doing it fully, reliably, and quickly. Part of that is because this entire checklist process is very manual. And I think it would be a significant improvement if all of the check parts of this, check tire pressure, check brakes, were done for you automatically, right? If we could just automate the does this still work, then the cost and the complexity of running this checklist would drop dramatically. And that is actually the thing that we're trying to do with testing, right? As the thing that we're trying to get working, keep working rather, gets more complex, a car, a plane, a starship, a PhD's worth of research, the list of things that might have gone wrong gets longer and longer. It gets more time consuming and error prone. You're gonna need a better approach. You need run a diagnostic. You need generate alerts. And with that mindset, this is why you should write tests. By counterpoint, a lot of people say, don't see the point of writing tests, right? They got their software to work, they got their analysis to work, they got their script to do the thing that they wanted, at least on the simple cases, right? They don't see the point of writing tests because they don't want to have to additionally prove that their code is correct now. But that misses the point, because tests are not about proving that your code is correct today. They're about proving that your code stays correct. Testing is about time, and thus testing is a matter of software engineering more so than it is about programming. If you are doing some very complex analysis, testing might still be a good idea, but it really, really shines when you have longer lived issues. If you want to make sure that this thing that you are asserting works, that the computation that you're talking about is correct, you need to have some sort of canned examples and push button automation for validating that. Tests are your protection against unwanted changes and regressions. Maybe you changed how your code works, maybe something changed below you. Tests give you this easy to trigger way of saying, is everything still good? If we're using protect me from change as a goal, then there have to be ways to game that definition though, right? Like you could say, just let me gather up all of the files in my home directory and say, this is the truth. If anything changes anywhere, the test fails. And that idea is unfortunate, right? Because you don't want it to prevent all changes. You just want it to prevent the changes that you don't like. And so what we're really looking for is some sort of mechanism to say, what can we do that produces a solid signal for this is still working correctly while not getting in the way of future changes? And that has a lot of nuance and suggests an important point, which is there's a difference between testing and testing well. Even in the upper echelons of the tech industry, testing is not universal yet, although it is much improved over the last 5 years. And a lot of the most common arguments against testing come from someone that had a bad experience, specifically because they had a bunch of bad tests and it got in the way. But amusingly, I think you can reason about the things that you want from good tests by thinking back to the Star Trek analogy, or just projecting yourself in the future, right? It's all about time. Imagine yourself forward a few years, imagine 5 or 10 years from now, and it's usually not too hard to envision the sorts of things that could go wrong. So I'll briefly mention some properties of good tests, right? You need them to be easy to trigger. The results are automatically available, or the result of a small effort. It's really nice to have a one command mechanism to check that everything is still good. They need to be fast, right? Your tests shouldn't take days to run. If they do, you have no idea whether or not the test results are valid by the time that you get those results back. And they need to be reliable, right? If the sensors say that we lost power on deck 3 randomly every few minutes, that's not helpful at all. If your tests fail non-deterministically, that's flaky. And it's bad specifically because it trains your team to ignore the test. And they have to be actionable. If a sensor goes off for no good reason, that's also bad. Consider how annoying it is when the smoke detector goes off in your kitchen. Most of the time, it is detecting smoke, but in practical terms, it's a false alarm because it's not actually an indication of a fire, right? So you want to make sure that these things are actionable. There's some secondary characteristics in here, and there's lots of scholarship in the software engineering, testing, and DevOps communities on what it means to write good tests, how to balance conflicting goals. But I'll summarize it with this. The single highest return on investment that you're likely to have in terms of ensuring that things are working as expected over time is to commit to good testing habits. In the previous talk from Mandy, the discussion of validating the sort of end-to-end results there, that is effectively manual testing for the whole system. And you can make your job and Mandy's job much, much easier if you're testing all of the individual parts as you go. I would almost guarantee that you're going to have fewer cycles to get something that actually reproduces properly if you can commit to this sort of thing early on. Another thing that matters is to be very aware of what version of things you're using. That is, one way to have reproducible results is to have a reproducible pipeline, a reproducible build. Some of the discussion here is focused on containerization, and that's one thing that you could do. And containerization will help because you can fully enumerate and reproduce the exact infrastructure that you're depending on. But it's tricky, right? You do want these things to be hermetic because nothing is actually quite as robust or correct as we pretend it is. In the opening keynote, we talked about, and in computing, we have purely reproducible results, and that's true-ish, but at scale, things do go wrong in computation. There are bugs in your processors, and they will come and go between processor versions. There are bugs in your operating systems. There are bugs in your languages and libraries, the dependencies that you're using. There are bugs in everything. Honestly, probably don't panic too much. The lowest levels, like your processors and your operating systems, are more likely to manifest as security and privacy issues rather than data correctness. But it has absolutely happened. We do find bugs in CPUs, especially when two esoteric bugs intersect. Floating point handling is a particularly common source of issues, which should be a little daunting for most scientific researchers because there's an awful lot of floating point computation going on. Testing is, again, a good frontline defense for have new bugs or the resolution of old bugs changed the behavior of my analysis in a way that matters. This sort of goes back to this wiggling idea. Another really critical part of this is to be as clear as possible about what versions of all your dependencies you built and tested and published against. We saw this in the first session. If you're writing a bunch of scripts to do your data processing, you probably want to be really, really clear about what version of your stats package you're using and what dependencies that is relying on. And that can feel really tedious. If you have the option, rather than trying to do this after the fact enumeration of everything you're depending on, you might make the switch to a better build system, which is a weird and very software engineering suggestion, but a quality build system models a functional programming language. And my Google bias shows I will reference this as Bazel, but there are several. All that really matters is you can have hermetic and reproducible builds with a full understanding and awareness of what the inputs and outputs of each stage are. If your academic automation systems are anything like mine back when I was a grad student, there's a lot of shell scripts in play and maybe a make file somewhere. And that's a very common progression for automation and pipeline sorts of tasks. The problem is that you run up to maybe even to the make file level and there isn't an obvious next step. You can identify that when file A is out of date, there's a recipe for rebuilding it. But there's no constraints on that recipe, nothing that prevents it from being deeply tied to your home directory layout or the particular set of tools or libraries that are installed on your computer. And that's going to make it really hard for anyone else to run that. The next sort of step in this progression is both magic and surprising. You want a build system, you want a pipeline system that isn't built on those arbitrary recipes, but one that tracks the entire set of inputs and outputs for every step in the process. A build system that models a functional programming language can make it perfectly clear what, if any, resources on your local computer are involved in your build and data processing. It will additionally give you far better hygiene, more reproducible builds, less wasted recomputation. Your research results deserve better than to depend on the particular version of Python that you happen to have installed at the time, especially if your analysis, like mine back in the day, is itself also depending on some other people's research code that may or may not have tests. A functional build means you never have to clean your workspace, right? Caching can work. If you're in a lab environment, it's very easy to set up a distributed build and make everything go faster. It's a thing that sounds exotic and silly, but I cannot overstate what a difference it could make in the long run. I wasted more hours waiting for a build in the 2000s than in the 2010s. And in the 2010s, I was working at Google on things that are used by hundreds of millions of lines of code. Build hygiene, build health is a real thing. Hermeticity and reproducibility start at the very bottom levels. We need to kind of push that a little bit, I think. There's some really nice blog posts about this intersection of modern build systems like Bazel and the sorts of data processing pipelines that underpin so much software-enabled research. I'll summarize with, starting your work with a build system that models a functional language like Bazel will give you a much, much, much better understanding of what tools and libraries and data are involved in your results and give you a better handle on when things actually need to be recalculated. You aren't really going to get to reproducibility, I think, without that sort of understanding. Finally, and briefly, if you're concerned about ensuring that things also work smoothly over time, like, hey, I did this analysis, it sure would be nice if I could also reproduce this analysis in 3 years or 5 years or 10 years. Be mindful of what external dependencies you are relying on transitively. That's Python and PyMath and et cetera, like all the way down the chain. In the programming domain, if you're just trying to hack together something and get a result, if you're trying to explore your research data and figure out where there might be interesting results, then depending on any random open source project is generally fine, barring security issues or bugs, right? If you can get it to work, you're golden. But if you need it to work over time, trying to make things that last longer, that becomes less and less true. Many open source projects, well, no, some open source projects are built with compatibility and sustainability in mind. They change APIs very rarely and very carefully. Others are experimental. They're trying to prove something, either a result or a design, and they make no guarantees about compatibility from version to version. If you keep the scale of your software very low, you'll probably get away with being sloppy here, but only probably. Unsurprisingly, building your research on top of a bunch of experimental versions of things is kind of risky. If you need to dust it off in 5 years, you probably won't be able to reproduce anything because you probably won't get it to build anymore. That's unfortunately difficult. I regard this whole problem, dependency management, as sort of the fundamental challenge in software sustainability right now. There are a lot of things that sort of kind of work, and some options that work in theory at scale, but no practical answers in the middle. In the end, I think research code is a particularly interesting microcosm of the programming versus software engineering dichotomy at large. As a scientist and a researcher, you're more likely than most people in tech to be working, at least some of the time, on code that can just legitimately be thrown away, that might not survive the week, that might not be seen by anyone else. You need to experiment and iterate. Some of the professional practices aren't necessary and won't pay off. But once you do get to the point that you need all of that cleaned up and shareable and reproducible, then the problem changes subtly. A programming project isn't going to give you any assurances that this code works in 5 years or on another researcher's computer. The highest value change is very likely to add tests. Testing done well pays off very quickly in days or weeks and gives us a solid and reproducible way to check that the results produced by another installation of your software are doing the right thing. Even if your research software isn't as complex as a Starship, the same principles apply. Fast, reproducible, reliable signals for all as well are invaluable for maintaining any complex piece of technology. If you clear that hurdle, spend some time thinking about how reliable your build is. What would it take to produce the same binary that you're using for your analysis 5 years from now? What subset of those inputs do you trust to not change or to change only in compatible ways? A higher quality build can reduce your exposure to hidden dependencies, and largely we all need to worry a little bit more about the reliability of our software dependencies. Like any change in dimensionality, moving from 2D to 3D or from squares to cubes, from velocity to acceleration, shifting from programming problems to software engineering ones is surprising and unintuitive at first. There are new norms, there are new ways of thinking. The first step is to recognize that your problem has changed and that you need not only tentative results, but reproducible ones. And I wish you good luck on that journey. To maybe help you with understanding these ideas and techniques in more depth, I'm also happy to announce that we're making electronic copies of my recent book available to all participants in this seminar. I believe you'll be emailed a PDF after the event. It's available under Creative Commons, so you're free to share that around and redistribute. It should go into much more detail in all of the things that I have just mentioned, and I hope you find that helpful. And we'll take time for questions.
Thank you so much. This was really great and I think really valuable. I feel that often here, like in this like research circles, you're kind of like an echo chamber and then we like bouncing the same ideas, but I think that you brought in some like really interesting perspective and it was very great talk. Thank you so much. So maybe I have one question here. I see we already have one question in the Q&A, but maybe first one is like, how do we make this build like robust? How do we ensure this? And do you have any thoughts on encapsulation? Like, yeah, I mean, we do use some of the like Docker containers and virtual machines. So I don't like, do you have any thoughts on that?
I think that the shift towards Docker and containerization is really valuable for a lot of the same reasons, but that will give you, hey, I'm sure that we can get the same result, not necessarily that like, but you're getting that by taking away all of the wiggle, to use a term from earlier, right? And I think a higher signal version of that is to actually have a principled understanding of that whole processing pipeline. And it shouldn't be the case that changing versions slightly hurts anything. The software engineering, like the tech industry is moving, well, slowly, but we're like putting a lot of thought into how to do all of this, how to, I have some software that I need to run. Here are the direct dependencies of it. Can I pull those in? Will they continue to work together? Will they continue to work together over time? I think given the option of a container that has been basically in stasis for 5 years, or something that just has all of its dependencies well understood and will work with the version of Python 5 years from now, I would rather the latter. I'll take the former, like you will at least get good results out of that for sure, but I'd rather the latter. And I don't think that it's actually asking a ton more overhead. Like I think most of these things will probably pay off even in an academic sort of research environment if your project is running longer than a month or two.
Yeah, I mean, an interesting problem because there is some research software that is like constantly active and that like stays alive for a long time, and there are also like these small kind of projects that are just being encapsulated and just
Yep.
like this maybe stay like just preserved for some
Yep.
for some future use, but ultimately they kind of like their lifetime is not super long.
Yeah.
So one question then from the Q&A, and I think it kind of like then like exactly extends this question. So does that mean that we need to keep dependencies up to date over time? And how does Google handle that?
Ideally, yes. And we don't do as great a job of that as we'd like to. It is a sort of, like I said, it's an unsolved problem in some respects. We certainly keep the most important dependencies up to date. Anything with security problems or any like major stuff like upgrading between language versions. Like you try to stay on the current version of Python and R and C++. Because if you're going to be around for 5 or 10 years, you're not going to really be able to justify being pinned to whatever version you started using 5 years ago or 10 years ago. And if your results disappear when you upgrade, like that's highly suggestive of many problems, right? Like, so like, yeah, you kind of do need to do that. I'm not going to argue that it's the most important thing to do. I think it's probably more important if you're modestly sure that your code is going to be reused 3 years later. Then making sure that you can use the current versions of things is real important. If it's a like one-off thing and you're done in 6 months, don't worry about it.
Okay, thank you. Yeah, that's interesting. Yeah, these migrations to like high version that then breaks everything is like always
Yeah.
a lot of work.
Yes,
Okay, so
exactly.
one more question. So thoughts on the data versus code dichotomy? I'm not sure if I'm pronouncing this well.
Dichotomy, yeah.
Okay. Yeah, is that a helpful stance, or should, for example, data be tested in a similar way as code? That's a good question.
It is a very good question. I think it depends still. One of the things that I say in a lot of sort of software engineering talks is, I had a quote one time from a colleague that said, accountants still have meetings and talk about their best practices. Accountants are mentioned in the Bible. Software engineering is 50 years old. Like, give us a minute. We're still figuring it out. And I think that's very true when you get into like specific subtopics in testing. Like Google has only known like, oh yeah, we actually really have to write tests for maybe 14, 15 years. And we've only been good at it for 5 or 10. So some of the nuance is still like, no one knows. I think there are many cases where, yes, treat your data as code is probably completely correct. There are other cases where it's not quite as clear cut. I think the most important sort of big picture outcome is you really want your results to be valid. And in order for that to be the case, you need to have recorded how your data was collected, what your raw data is, and then be able to reproduce all of the steps of the pipeline there. So yeah, probably check in and make public the raw data as well as all of the steps in the pipeline and the build. As far as testing on that goes, this is a harder question. And like there are arguments, I think, on both sides of it.
Yeah, and also, I mean, probably maybe code is not going to work well if there is something wrong with the data set. So
yep, definitely happens.
Yeah, thank you so much for the great talk, and thank you so much for the discussion.